Okay, so here, let's see the additional example. Actually, this is the problem 11 in the problems behind the chapter. If you have the textbook, you can find it out. So actually, it says the volume charge density is a solid non-conducting sphere of radius r, capital R, varies with the radial distance. Small r is given by rho. Actually, this charge density is not uniform. It is related to the radial distance. So for the first question, what is the sphere's total charge? So as much as it is not a uniform distributed charge, you cannot just multiply the density by the volume. Not that simple. We actually need to use some integration to find the total charge for this sphere. Okay, so actually, we'll write it like this. The total charge for this sphere will be a triple integral for this sphere, and then we have this rho. Rho is this one. Rho is this one, and dv, which is something like you have a sphere here, sphere in 3 dimensions, although I can only draw it in 2 dimensions. And actually, the rho for every part, is different. It's different. Just say, for example, if we choose this part, we have something like this. This is out from the center, from the center point. So this is actually dv, and within this dv, we can have a rho, which can be considered as a uniform within this small cube. Actually, it is not a cube because this is a sphere. If we really use the Cartesian coordinate dx, dy, dz, then yeah, in this case, we can write a dv easily, which is like a dv equals dx, dy, dz. But the lower and upper bound will be difficult to write because the integration will look something like from 0 to r squared minus x squared minus y squared, something like this, and then integration for something else, and then integration for something else. Then this will be very difficult, or maybe even like square root of this r squared minus x squared minus y squared, something like that. So actually, we will use the spherical coordinate here. Spherical coordinate, SPH, spherical coordinate. Okay, so actually this dv will look like this. The triple integration, and then we have this this number. Maybe we can just call it rho s at this moment, because every time y 35.4 pico will be tedious. So let's call it rho s at this moment, and then r over capital R, which is actually this rho. And for dv, we will have something like this: r squared sine of theta, dr d theta d phi. So you may ask, what is these terms? Okay, actually you can just check it out on the Wikipedia if you are interested. Yes, actually in calculus class, you may need to remember something like that. Actually, this is an example for the spherical coordinate. So maybe you can just simply remember that. But actually, I do not go through the derivation deeply. I just let you know what you need to know for this example. So for the spherical coordinate, compare with the Cartesian. For the Cartesian one, we have x-axis, y-axis, z-axis. And actually, the spherical coordinate can be regarded as a generalization of the polar coordinate. So suppose we have a point at here. So if we just project this point into the xy plane, then the xy coordinate will be something like the polar coordinate. And the remaining one is the z coordinate. So actually we have theta. Theta is the angle between this line with the z-axis. And then when we project this point into the xy plane, this line, the angle between this line and the x-axis will be the phi. So we have two angles, and this is the distance from the origin point to that point. So R, it will be nothing but square root of x squared plus y squared plus z squared, something like that. So using the Pythagorean theorem. And actually you can imagine that, yeah, so this theta will be something like this length divided by this length will be the tangent of theta, and so on and so forth. And maybe, yeah, this line, which is actually this one here, divided by this one will be tangent of this angle. So actually you can find the relationship like this, So this is r, this is theta, this is phi with the Cartesian coordinate. And how do we get that term will be related to the Jacobian matrix? Actually, yeah, so the Jacobian matrix will look like this when you convert the xyz into the r, theta, phi coordinate. Then this is the Jacobian matrix. We need to take the determinant of this Jacobian matrix. Then you will know, this is the term when we need to convert the dx, dy, dz into this dr, d theta, d phi. Will have this term. Yeah. Or maybe simply speaking, let me try whether I can explain it. So, well, start. Right. Oh, okay. Okay. So suppose this is the original point, and then suppose maybe I should write it in the other way around, like this. So maybe this is x, y, and z axis. So suppose we have a dv, the volume somewhere here. Yeah. So actually we need to if we go to draw something, should be something like that. Actually, that. Okay. So actually we need to calculate the volume of this cube. And actually maybe for this one we will have something like r sine theta, and then it's something like you imagine it's a cube. So you need to find the height, the width, and the height, width, and the, yeah, I forgot it. Yeah, maybe, yeah, we need to find the length of the 3 dimension. So this dimension will be simply the dr, and then here will probably be r sine theta, d theta, something like that. R d theta will be somehow like the arc length, and then we need to take some sine theta to calculate the real length. And also we have, or maybe this is simply the RD theta. One line is the RD theta, and another line is R sine theta d phi, something like that. And then when we multiply all these 3 terms together, it will be actually this term. Or if you need to go more rigorously, you just go to the Jacobian. You need to know, then you know why there is these 2 terms here rather than this 3 terms. Or simply speaking, when you consider the dimension, this is the length this is angle, this is angle. So to complete the three-dimensional volume, we need these two dimensions. But why we get this? Just go to the Jacobian matrix. And of course, we need to determine the lower and upper bound for the integration. For dr, we can simply imagine this is from 0 to capital R, from 0 to capital R. And then for theta, it is the angle between this one and the z-axis. This theta can go from 0 to 180 degrees, from here up to here only, because how you rotate, the maximum angle can only be 180 degrees, which is pi in radian. And for theta, it is the projection to the xy plane, and then this the angle of this line between the x-axis, so that it can rotate from 0 to 2 pi. Okay, so this is roughly how the spherical coordinate works. And actually, after you write it out, this integration, although looks complicated, but actually it's very simple. We just need to separate the term, because we have this is the constant. This is also constant, and this is only related to R. This is only related to theta. So we can just separate them. Rho s over capital R is a constant, and then we have totally 1R R squared. We have totally R cubed dr, and then integrate from 0 to capital R, and then we have a sine of theta d theta. It is integrate from 0 to pi, and then also we have a d phi, integrate from 0 to 2 pi. So it's just integrating 1 from 0 to 2 pi, which is very simple. So we have this one will be R to the 4th power over 4. Very simple. This is negative cosine of theta, evaluate from 0 to pi. So it will be 1 minus negative 1, which is 2 here. And then for this one, integrating from 1 will be 5, evaluate from 0 to 2 pi will be 2 pi. So it is so the integration is easy, although we need some fundamental knowledge to really get this triple integration. So the final answer will be pi rho s r cubed, and then we can just substitute the number. Pi is 3.14, and then rho s is 35.4, pico is 10 to minus 12, and then times capital R is 5.6 centimeter, 5.6 centimeter, so which is 0.056 cube. Okay, so this is 1.95 times 10 to minus 15 coulomb, or you can write it as a 1.95 femtocoulomb. So this is the total charge on this sphere. So I think the difficult part is dV equals this one. If you can't really understand, you can simply remember this, because when you learn calculus, usually there will be only three coordinates. One is the most simplest one, the Cartesian, dx, dy, dz, and other one is the cylindrical. So which is like the polar coordinate with the independent z coordinate. So it's still easy to manage. And the most difficult one will probably be the spherical coordinate. So yeah, like this. So let's go to the second part. What is the field magnitude E at B, R equals 0. Okay, so of course, okay, so yeah, so okay, for this chapter is about Gauss law, so you can simply imagine we need to use Gauss law for the remaining part of this example. So for part B, when R equals 0, you can imagine you have a sphere like this, and then you draw a very small Gaussian surface, and the R tends to 0. R tends to 0. So it should enclose nothing. So Q enclosed for this Gaussian surface should be 0. And due to symmetric, you can quickly find that E should be 0 for R equals 0. So usually when it asks R equals 0, 99% the answer will be 0 for the E field. And then for part C will be a difficult one. Yeah. But yeah, actually just as difficult as the part A. So now we consider R equals capital R over 3. And suppose this is the Gaussian surface. And actually we need to find the Q enclosed in this part rather than the capital Q. Capital Q is the total charge on the whole sphere. And here we need to consider the Q enclosed within the sphere with radius capital R over 3. So here we slightly need to repeat the calculation in part A, but with a small modification. Here we still have rho s over capital R, and then we still have R cubed dr, the same as before. And here we still have a sign of theta d theta, and then we still have a d phi. So we need to also determine the lower and upper bound. As much as it is still a complete sphere, this angle is still from 0 to 2 pi. This is still from 0 to pi. Nothing changed for those two terms. But for this one, we only consider the sphere within capital R over 3. So we only integrate from 0 to capital R over 3 like this. So this integration will be a little bit different. This is R over 3 to the 4th power or over 4 like this. Because originally it's R to the 4th power over 4, but here we only evaluate up to capital R over 3. So we have capital R over 3 within this 4th power. Okay, this term is still 2. This term is still 2 pi. So the answer will be okay, so maybe we can just, maybe we can still keep this as small r. Maybe we can still keep this as r, because for part E, we still need to graph the E versus small r. So yeah, so let's just keep this as small r, and then we get this expression when the r change from maybe 0 to capital R. And then after we get the general solution, and then we plug in R equals capital R over 3 to get the answer for this one. but finally we can still draw the E for the over the R axis. So actually we still have a small r here. Okay, and in this case we will have this is rho s, this is r to the fourth power, and then this 4 and this 4 will be cancelled, and then we still have pi over r like this. Okay, so actually we need to calculate Q enclosed when R equals to capital R over 3. So we can plug in here. So we have rho s and then capital R over 3 to the fourth power pi over capital R. So we have a rho s R cubed pi over 81. And here we can use the Gauss law. Q enclosed R equals capital R over 3 will be rho s R cubed pi over 81 should be equals to this integration E dot dA. So suppose because it is still symmetric for different angle, so the E field should still be uniform over this Gaussian surface. So we can write it as E times 4 pi R squared, which is or maybe at this moment we can still keep R. I think we can still keep R. So I just remove this part. Maybe. So we still keep this. So I still keep this as. So I still keep this as rho s to the R to the fourth power over capital R like this. So equals 4 pi R squared like this. And I forgot this epsilon naught here. So I still have epsilon naught here. So this is the Gauss law, and then this is the Q enclosed when the radius of the Gaussian surface is small r. And then here we can just move this term over and then make some cancellation. We can have E to be rho s, and then we can make some cancellation. This R squared and R to the fourth power can be partly cancelled. This pi and this pi can be cancelled. So we have rho s R squared over epsilon naught capital R. We still have this 4 here. 4 epsilon naught like this. Should be like this. Okay. So this is the general solution when R is the variable. So now we need to determine E when R equals capital R over 3. So it will be rho s R over 3 quantity square over 4 epsilon naught capital R. So this will be 36 epsilon naught rho s R. This R square and R can be partly cancelled. We have R here, rho S. And then here we have a 3 squared times 4, which is 36. And then epsilon naught here. So we can just plug in the value. We have 35.4 times 10 to minus 12. And then multiply by 0.056 over 36 times. Epsilon naught is 8.85 times 10 to minus 12. Okay, so this number is 6.22 times 10 to the minus third power Newton per Coulomb. Okay, so this is the answer for part C. So here we make use of the Gauss law. We first need to determine the Q enclosed within this Gaussian surface, and then we apply the Gauss law for this Gaussian surface. We have a Q enclosed equals epsilon naught times the net flux. So the net flux, we assume the E field is uniform over this Gaussian surface. We make this double integration to be E times the surface area. So finally, we can get the closed form expression for the E field when R is a variable. And finally, we plug in the small r to be capital R over 3 into this expression to find the specific solution to this question. Okay, so let's move to the next part. So here, when we consider R equals capital R, we can make use of a capital Q, which is pi rho s R cubed, as we have derived it in part A. So using the Gauss law, we can have epsilon naught E times 4 pi R squared. So this is the net flux, this is the epsilon naught equals the total charge. So this is actually we can just move these terms over. We will get E to be sorry, this is capital R squared. This is capital R squared. Capital R squared. Okay. So actually we can partly cancel this R squared. We have pi rho s and then R over 4. No pi. Pi can be cancelled. So we have 4 epsilon naught like this. Okay, and then we can just plug in the values. 35.4 times 10 to minus 12. And then this is 0.056. And then over 4 times 8.85 times 10 to minus 12. So this number will be 5.60 times 10 to minus 2 Newton per Coulomb. Okay, so this is for part D. Part D. And actually, we can also derive the closed form expression when R is larger or equal to capital R. When R is when small r is larger or equal to capital R, then we still have Q. Q enclosed is still Q. If we consider this is the Gaussian surface, this is the sphere, then we still have Q to be pi rho s R cubed equals epsilon naught E. Here we have 4 pi R small r squared because we consider the radius of the Gaussian surface. So we have this term. And in this case, we will get E to be rho s R cubed over 4 epsilon naught small r squared. This is the closed form solution when R is larger than or equal to capital R. this part. So this may not be necessary for part D, but will be useful for part E. So as much as we get this expression, and also this one, we can actually go to the part E. We can actually go to the part E. So here for part E, we have E to be rho s times r squared over 4 epsilon naught r squared r. And then when r is smaller than r, when r is larger than or equal to capital R, it is rho s capital R cubed over 4 epsilon naught r squared. So we can actually graph this out like this. So here we have capital R here. And then when R is smaller than capital R, it is proportional to R squared. So it is increasing like this, This is proportional to R squared. So for this one, it is inversely proportional to R squared. So it will look like this. This part is inversely proportional to R squared. And of course, this point, we have E. This is R. This is 0.056 meter. And this point will be 5.6 times 10 to the minus second Newton per Coulomb, like this. So this is the graph.